and this direction you have. So ultimate, combining these two bonds, the resultant dipole moment this direction. That means water molecule, this one, have a dipole moment, right? So dipole moment, and whenever you have dipole moment, that's we call polar molecule. Okay, so that we call polar molecule. So whenever you have, so do you understand that? Let's see one more example. Let's say nitrogen, lone pair, you have hydrogen, hydrogen, and hydrogen. Again, so between this hydrogen, nitrogen, this direction dipole moment, this direction dipole moment, this direction dipole moment, resultant direction, this one. So mu greater than 0. So there you have a dipole moment, right? This is the fundamentals that based on a chemical bond, okay, based on a covalent bond, there could be a charge separation depending on the electronegativity, and we can have a dipole moment. Okay, so if that is the case, if we understand this one, let's take example on this one. So between CHCl3 and CFCl3, which one will have higher dipole moment? So that means let's take example that carbon. If we compare these two molecules, so carbon you have hydrogen, Cl, Cl and Cl, and the other molecule carbon you have fluorine, Cl, chlorine atom, chlorine, and you have a chlorine over here. So which one has a higher dipole moment? That's our target. If we understand the previous concept, then you can answer. So that means for this particular case, you have this direction. For this bond, this direction, this bond, this direction. So resultant, you have dipole moment this direction, correct? But the second case, again, chlorine is more electronegative than carbon. So this direction you have dipole moment, this direction, and fluorine also more electronegative, so that direction. So previous case you have one direction, the vector, but here 3 carbon chlorine bond acting this direction and fluorine acting this direction. That means actually the higher dipole moment should have over this molecule chloroform, because somehow because 3 people are pulling electron this direction, so you have a dipole moment. But here 3 people are dying direction, one bottom direction, but there is another electronegative atom, fluorine, pulling electron that direction. That means somehow neutralizing some amount of force. That means this will have higher dipole moment than that one. Similarly, if we compare these two, so that means we have to have idea about the structure. That nitrogen you have NH2, okay, so that means CH3, H and H, you have a lone pair over here, and you have a N double bond O minus, and a CH3. Now between these two, which one could have higher dipole moment? So we know that for this particular case you have dipole this direction. This particular case you will have this direction. Already you have a charge separation. That means the dipole moment higher for this one. Okay. Now this is very interesting case, that for carbon dioxide and sulfur dioxide, so carbon dioxide C double bond O, and sulfur dioxide S double bond O. Now both of them have 2 lone pair. So which one has a high dipole moment? That means based on our previous discussion, dipole moment this direction, dipole moment this direction, here this direction, here this direction. So this particular case, you have a dipole moment mu this direction. So mu not equal to 0 over here, but here mu equals to 0. That's how, taking some smaller compound example, that to realize that in a bond how it works, the dipole moment or charge separation. Very important concept, dipole moment. So if we understand this one, how about this example? So this particular case, we can see.
That last one, can you scroll up just a little bit? You're going a little bit too fast.
Yes.
Okay, thanks.
So that means let's take a look. This is very interesting example to understand the dipole moment, that you have carbon chlorine bond. So dipole moment this direction and dipole moment this direction. Why? Because chlorine is more electronegative than carbon. So chlorine electronegativity is 3, right? So 3 and carbon 2.5. So that means resultant dipole moment is at this direction. For this particular case, this direction dipole moment, this direction dipole moment. So resultant dipole moment this direction. Makes sense? But this particular case, you have dipole moment this direction, here this direction. So here mu not equal to 0, here mu not equals to 0, but here mu equals to 0. Because what I said, that two dipole moments, they're acting opposite to each other in equal magnitude. That's why mu equals to 0 over here. But here, in this case, that means you have a resultant dipole moment. So here mu not equals to 0. So these all those four structure, they are isomer, not isomer. So these four structure you can see based on the position of atoms, it can be polar or non-polar, right? So even these two molecules are same, but you can see one is a, comparing this one specifically, mu equals to 0 because of the orientation of the vector, dipole vector. I hope you guys have that understanding about how it works. Because before I move to next concept, I have to make sure that you understand that particular concept, that electrons in a covalent bond, they can be towards one specific nucleus or atom based on the electronegativity values. If we understand that, then we can think something new, interesting. Okay, so that means the electrons in a bond, they can be dragged. Okay, so that means in this particular case, so you have bond carbon, 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 chlorine. So in this particular case, we just discuss about one particular bond, but in this case you have electron density towards this direction because it's more electronegative than carbon. So not only this bond, you can think about that electron can drag from this bond as well, this bond and this bond. So this one delta minus, delta plus, delta double plus, delta triple plus. So that means what I want to tell you the information that because of electronegative atom here, chlorine, the electrons through the bond, they can be like one way they are like pushed out, right? So same way, if that is the case, chlorine with, so this is particular case, that means this particular bond electron is dragging towards the chlorine because the chlorine is more electronegative, right? So why I want to introduce that particular stuff? So based on that, we call inductive effect. So based on electronegativity, we understand dipole moment, and now I'm saying something that inductive effect. Okay, so inductive effect means displacement of electrons through the bond. So this is not only through bond, it can be through space as well, like displacement of the electrons because of the presence of electronegative atom or groups. Okay, now I said electronegative. So that means you understand this concept that okay, chlorine is electronegative, so it is dragging electrons, right, from this bond, and it can, this effect not only for one, it can be over here, right? So then let me show you that how it works.
Professor, would you mind defining inductive effect one more time for me, please?
So the ability of the presence of the electronegative atom, let's say fluorine, chlorine, bromine, iodine, okay, or there are some groups. So presence of those groups, the electrons from the molecular bond, they can be pushed towards one direction. So those kind of effect we call inductive effect. Let me show you one complete slide so that you can understand this one. So here, okay, so here you go. Okay, so you can see that means the dipole moment, like the bond polarization caused by an adjacent polar bond or a group, is known as inductive effect. because you are interested here. So what I'm saying here that a bond polarization caused by adjacent polar bond or a group is known as inductive effect, and that can be classified into two. One is electron withdrawing effect and electron releasing effect. Because if we have some groups or atom that can pull electron, that means electron withdrawing group. Example here, nitro NO2 nitro group, or cyanide, or carbon dioxide, carboxylic acid, see, halogen atoms, fluorine, chlorine, bromine, iodine. So those are the electron withdrawing group. If they are connected with the molecule, the bond, so they can drag electron towards that particular site. So this is called inductive effect. Or if you have a plus group, so plus group means the atom or group which can push electron. Okay, so if that is the case, we have electron releasing effect, okay, or electron donating. So that means what I want you to like take a short note that what are the groups are known as electron withdrawing group, and what are the groups are electron releasing or donating groups. So this is a list of group we have to remember, okay, memorize. So that means if that is the case, now we'll go to interesting. Okay, so that means we understand that what is the inductive effect means, right? So presence of some atoms or groups, you can have a bond polarization, right? Like bond polarization. So bond
Um,
polarization means,
I have a question.
yes.
Oh, sorry. So like I know you did the example with like the carbons and the chloride, but like if you did like does it matter how many carbons there are? It will still not be affected by like the chlorine.
Of course matter. So if you have instead of one, if you, instead of one chlorine, if you have more than two or three, the effect will be more. Very good question. So we have some example we'll discuss right after this slide. So how this is matter, like if you have more number of electron withdrawing groups or atoms, then you can have more inductive effect, right? Is it clear?
Yes, yes. Thank you, Dr. Manna.
So yes, thank you. So let me give you one example there why it is important to understand inductive effect. Okay, what is important, let me share. I mean, so basically step by step, think about electronegativity induces the dipole moment, and from that we understand the inductive effect. And now I'll show you that why how it is a so important concept to understand acidity and basicity. So here are three examples, give you like detailed idea about the importance of inductive effect. Okay, so that means if I redraw these three molecules, one, two, three, double bond O, bond OH, and you have a chlorine atom over here. Now, second example, Cl, bond, double bond O, bond OH. Third one, chlorine, double bond O, bond OH. Now, as we know that chlorine has electron withdrawing group, that means atom, so that means electron is dragging this way, this way, this way, this way. So this way actually through bond, chlorine, by the inductive effect of chlorine, you can see the electrons are pushing this direction. If that is the case, if you understand this one, then what is going to happen that, so this bond will dissociate, simple. So this bond will dissociate. Make sense what I said? Because I explained you that electronegativity, dipole moment, and inductive effect. So based on those three concepts, we can see that this particular molecule, chlorine, has minus I effect, right? Minus I effect. So it is through bond, okay? Through bond, it's a dragging electrons from this particular case. So if that is the case, so if this bond breaks, what do you get? We get double bond O minus. Now think about OH, this particular bond, how many electrons you have? 2 electrons, right? So if 2 electrons come over oxygen, now become minus and plus H plus. H plus we call proton. Is that make sense? Like organic chemistry interesting here that because of this inductive minus I effect of chlorine through bond acting, it is acting through bond, and you can have a dissociation of OH bond, and you are forming this species and H plus. Now look back the original chemistry, what we learned. If a substance or molecule or chemicals which give H plus, we know that's the acid. We have three different theory: Arrhenius theory, Bronsted-Lowry theory, and Lewis theory. Three different theories there to explain the acid-base concept. So here we can see that this particular molecule, you can have H plus over here. That means this is the acid, right? So this will act as acid because it can give H plus, okay? I mean, there are some compound you can apply both the principle, but in this particular compound, I'm saying that, okay. How about second one? The second one, similarly, we can see that, okay, so electron are dragging this direction through bond, right? So this direction, you have the inductive minus I effect. So this will again dissociate to Cl double bond O minus plus H plus. But the question, what is our goal? Our goal is this one versus this one versus, I mean, these three. We have to compare the acidity. We understand that based on the sorry. So based on the inductive effect, we see that, okay, that's the bond dissociation. Okay, I mentioned over here there is a bond dissociation. Okay, so bond dissociation you get when you have bond dissociation, we call conjugate base. So if this is a acid, after bond dissociation, whatever species we get, the remaining negative charge species we call conjugate base. So that means we understand what is the acid and conjugate base means. Similarly, this one is your conjugate base. Okay. Now here again, if you consider this molecule, same way you can have this is a reversible sign. So you can have a Cl double bond O minus plus H plus, right? Clear? But the interesting part over here, which one is more acidic? Most acidic between among three molecules, which one is most acidic? So most acidic compound is this one, then this one, then this one. So if we arrange, let's say 1, 2, 3, the acidity order 1 greater than 2 greater than 3. Now why so? That's the role of inductive effect. Here chlorine is close to that particular bond, this bond dissociating, this bond dissociating. So here chlorine atom close to that bond, right? 1, 2, 3 bond apart. But here chlorine 1, 2, 3, 4 bond. But here chlorine 1, 2, 3, 4, 5 bond apart. That means with increasing distance, the inductive effect of chlorine decreases. Is it clear? Very interesting concept that I repeat again, that because of the electronegative atom chlorine, increasing distance, the inductive effect decreases, right? That's why I say the acidity order is this one.
I have a question.
Yes, please.
So does the chlorine not draw any electrons from the
No, I didn't get your voice. Can you repeat one more time, please?
yeah. So can you hear me?
Yeah.
Okay. So does the chlorine not draw any electrons from the double bonded oxygen?
Okay. So basically, I mean that's true, but the thing is, these two actually equivalent. I mean, that H actually can move to over here, and this become C double bond O. So that's why we should have knowledge about functional group before we talk about acidity. But anyway, syllabus is like that. So okay, but first consider that this is the like single bond, covalent single bond. So this bond will dissociate. Okay, first, and you get this kind of like order by using the knowledge of inductive effect, how it works. So that means the message over here that the message over here that with increasing distance, inductive effect decreases, and because of the inductive effect, you can see the molecule can have like acidic hydrogen. So that is the term I want to acidic hydrogen, right? So now someone asked me question about just now that what about if you have more than one fluorine atom, right? So let's consider this one. So you can see again, so this particular structure, fluorine, carbon, fluorine, fluorine, double bond O, O, H. That means this particular case, we can see instead of previous example, one fluorine you have here. So that means this direction, electron is dragging this direction, and so three fluorine atom actually like have a stronger inductive effect. Okay, so that means this bond can easily dissociate, right? Now the same for the second example, you have fluorine, carbon, fluorine, fluorine, and you have say double bond O, OH. Okay, so we already understand that. Okay, that means this way electron. Okay, so if we compare these two, which one is more acidic? Anybody want to try? Which bond can easily dissociate? Compound 2 or compound 3? Let's say 1, 2, 3, 4. Both has equal number of fluorine atom, both of them, right? But which one will dissociate faster? Anybody?
Is it number 3?
Of course, very good. Because you can see the distance from this particular bond where you are dissociating, this bond dissociating, right? This bond. So fluorine are close, 3 fluorine are close to that particular bond, 1, 2, 3, 4. But here, 1, 2, 3, 4, 5 bond distance. Okay, so that means we can understand that, okay, 3 has higher acidity than 2, right? 3 has higher acidity than 2. Now if we compare, basically 1, if you think about 1, so 1 actually don't have any electronegative atom, so this is means CH3, that means the lowest acidity will be 1. Now 4, where you put 4? 4 will be here, because chlorine is less electronegative than fluorine, right? So that's the order of acidity. Okay,
Can you explain one more time how you counted those bonds and how it's shorter, please?
counted bond. Okay, so see, from this particular carbon and fluorine over here in the second, so this is called alpha carbon. Okay, so now actually there are few things, alpha, beta, and gamma. So if the functional group directly connected to the carbon, we call alpha carbon. And so that means for this particular case, this is alpha carbon, this is a beta carbon. So here, this is alpha carbon. Okay, what I said, 3 things, alpha carbon, beta carbon, and gamma carbon. So now the one thing I want to message is that the functional group. So I didn't talk about that, what is the functional group, but here carboxylic is a functional group, C double CO2H, that's a carboxylic acid, and we call functional group. So the carbon directly connected with the functional group, we call alpha carbon. That means this is alpha carbon, this is a beta carbon. Okay, so now we can see that this particular case, fluorine are in alpha carbon, but this particular case, fluorine are in beta carbon. So that means in the beta fluorine, they have less effect on the displacement of electrons over here. What I said, so displacement of electrons. Okay, it makes sense now.
Yes.
So
Can you explain why one is the Least.
Because one, you don't have any electron withdrawing atom or groups,
Okay.
right? Very good, very good. Now are you guys getting? I understand. Okay.
On the question before this, yeah, with the pKa number,
Mm-hmm.
can you also use that to determine the acidity order? So like the least
Yes.
number is like the least or the most acidic?
Yes, of course. So I will explain.
Okay.
Let me give you some idea. Now I'll
Okay.
get back to the PowerPoint and we'll see one by one, so more detail. Okay. So let's
Okay.
go back to PowerPoint. Yeah. So that means we have some idea now. I'm trying to build up your concept that a molecule, chemical bonds, and followed by the electrons can move if you have pi electrons resonance, and then followed by dipole moment, and followed by inductive effect, and electronegativity and inductive effect. And now I am just giving you concept of acid and base for organic molecules. So how organic molecules, acid and base work? Okay, let's go back to PowerPoint and we can see more detail about this kind of stuff. Okay. Okay, so here, okay, so now I hope that all of you get some like feelings that how it works. Okay, so that means, so we know the definition of Bronsted-Lowry acid-base theory, that the acid which a proton donor, that means the molecule I just explained, those are actually acids because they can donate proton. Proton means H plus, right? And the Bronsted-Lowry base means the substance or the molecule which can accept the proton. That is the Lowry base, Bronsted-Lowry base, right? Make sure that we have a clear visualization about the acid base means in terms of Bronsted-Lowry theory, proton donor and proton acceptor, right? Concept. So proton means H plus proton, no electron. Okay, H plus proton means no electron. Okay, so if that is the case, let's take a little look. I introduced that H is the acid and you have a base. If you take this H plus means proton, the remaining molecular species, which is A minus, we call conjugate base. Very clear? I repeat again. Now this is the new term, new concept, that what is the conjugate base? What is the conjugate means? We know acid, which gives H plus, but once you remove H plus, the remaining molecular entity, I mean the species, that is the conjugate base. So now we understand two things. One, we understand that Bronsted-Lowry acid base, what does it mean in terms of proton, and also we understand the new thing, a new scientific word is the conjugate base. Okay, so A minus is the conjugate base, and after accepting H plus, whatever the molecular structure, that will be your conjugate acid. Make sure that we understand acid base, conjugate base in terms of this theory. Okay, all right. So here are a few examples. So water, H2O, water molecule, right? This is water molecule, and this is one example of base. And now think about if take this proton now become OH minus. So this is a acid and this is a base. What I said, after removing H plus, whatever the structural unit you have, that is your conjugate base. Okay. So make sure that we have clear understanding about what is the conjugate base. Very important to understand some stuff. Okay. Okay. So water actually not only acid, it also acts as a base based on the situation, condition. I mean, no. So right now here in this particular example, water acting as a acid. Okay. Now, similarly, we know that a hydrochloric acid, HCl, is an acid. The reason is HCl can give acid, right? H plus. That's why it's a acid. And after removing H plus, the Cl minus is the conjugate base. I'm pretty sure you got it. Okay. So that means we understand acid-base conjugate theory. Now, so general pattern that thoughts that if you have an electron-rich species react to the electron, the bases are electron-rich. Okay. So what I said, we learned acid-base. Now, if you have an electron-rich species, that will act as a base because it can donate electrons to make a bond with the H plus. That's why electron-rich species are base and electron-deficient species is the acid. Okay, so acid are electron-deficient and base are electron-rich. This is a general concept. Okay, so here are a few examples. We can see that HCl, or this is CH3 hydrolyzed, acetic acid, water, propionic acid, acetylene, H2, ammonia, ethylene, methane. So there are some examples that we can see those hydrogens are basically acidic hydrogen. That means they can, based on the condition, they can release H plus. Okay, I mean they can give H plus. That's why they are acid. And our goal is to compare the strength of the acidity. So now we understand if we have the substance or molecule can give H plus as acid, but how about the strength? How we can decide the strength of the acid? So that we can represent by pKa values. So here is the value, pKa value. So you can see that -7, it can be negative to positive, also can be 0, right? So the pKa value this way. Before I talk about pKa value, let's go back to I'll come back to this one later. Go back to the acid dissociation. That means if you have an acid, so you get a minus conjugate base. So this particular case we represent by acid dissociation constant or equilibrium constant. K equilibrium equals to product by starting material, right? And that's the expression of for if a acid you put in a water and dissociate like H plus and A minus. So that's the expression for K equilibrium. So now we know, if we know the K equilibrium and K equals to this one, right? Ka, which is called acidity constant Ka. Now, if you remember from the general chemistry that pH equals to minus log of concentration of hydronium ion, that's the definition of a pH. Similarly, now pKa means, if we know the acidity constant Ka, that means pKa equals to minus log of Ka, right? So now one fundamental thing to remember, that higher the Ka value, higher the acidity, but lower the pKa value, higher the acidity. Make sure you have a clear understanding about this particular term, that if we have a higher Ka value, like acid dissolution constant value, that particular substance or molecule higher acidity. But if you have a lower pKa value, that is higher acidic. Okay, I mean we are representing in terms of two different like expression. I mean two different mathematical expression, pKa and Ka. So I think we already discussed these things, right? So that means, just take an example. Okay, HCl -7 and acetylene 25. So if you compare pKa value between this and this, which is a smaller, so this is smaller, that means that's the higher acidic than this one. Or let's take another example between let's say, good example, let's say this is propanolic acid, and you have, so between these two hydrogen, which is more acidic? But definitely this one is more acidic because lower pK value. So by reading a pK value, we can figure it out the acidity of a compound. So here is some example that acetylene pK is 25, right? Whereas ammonia pK is 38. So that means you can think about that lower the pK, that means comparing this one with this one, that means this guy will have higher acidic because this proton is higher acidic, right? So make sure that we understand definition, I mean the concept, and how to read those pK value or pK value. And now we can move to the factors, the strength of acid, like what are the factors that can influence the acidity? The factors which can acidate, that's 4 factors: element effect, inductive effect, resonance effect, and hybridization effect. So I already discussed hybridization, so you know how it is. Resonance also we discussed. Inductive effect we just discussed today, and element effect. So the acidity of a molecule depends on 4 different factors. Element, okay? Now we'll see the example how actually it works. So when I say element effect, let's take an example over here, that H2O, water and methane, between these two red hydrogen, which is more acidic, right? How we can decide in terms of element effect? Now, if I remove this H plus, we have OH minus, right? If we remove H plus from here, now negative charge over carbon. Now, I'm talking in terms of element effect. Now, negative charge over oxygen and negative charge over carbon. So where it is more suitable? Because oxygen is more electronegative than carbon, so this is more favorable. So this one is more favorable because oxygen is more negative. That means this will be more acidic than that one. And now, this is very important, write it down, that we understand that, okay, this is acid and this is conjugate base. Now, higher the stability of conjugate base, that particular acid is more acidic. Stability of conjugate base is the big factor over here. Stability of conjugate base. If we can compare conjugate base and their stability, and then we can figure it out that which one will be the most in a relative acid strength. That makes sense. So now we can see in terms of element effect which one is more acidic proton between water hydrogen and hydrogen from hydrocarbon methane. This is more acidic because negative charge in the conjugate base over oxygen is a more stable, but negative charge over oxygen in compared to OH less stable. Relative strength, relative stability of conjugate base, that help us to understanding the effect of element. Now, how about other three? Okay, how about let's say other few example like effect of hybridization, effect of inductive effect, or an resonance. Okay, those we'll see. Let's see. Okay.
Did you say that the more stable it is, the more acidic it is, or is it the other way around?
More stable the conjugate base, corresponding acid is the more acidic. Okay.
Thank you.
In terms of element effect, I described that element means the negative charge over the element. So we are comparing two elements, oxygen with carbon. So that is the element effect, the stability of conjugate base. Now, how about in terms of resonance? I mentioned the four factors decide the strength of acid. Now, if we have these two example, okay, so that means if we have oxygen, OH, okay, so now if we dissociate this bond over here, we dissociate bond over here. So what I get? So I get 1, 2, 3, O minus plus H plus. Right? Agree? So this is the acid and this is a conjugate base. Okay, how about this one? This is number 1. How about the number 2? So 1, 2, double bond O, H. Same, if we break this bond, dissociate this bond, we get, sorry, it's too many colors. That means we get 1, 2, double bond O minus plus H plus. So this is the acid and corresponding conjugate base, correct? Now, what is the question? Question is which one is more acidic, or we want to rationalize the effect of resonance. Okay, now if we want to talk about effect of resonance, so this particular structure, I mean the conjugate base, this particular conjugate base, we can already see over here that if we have a negative charge over here, this will come over here, this will go over there. That means whatever we learned throughout the last week, whatever we learned, now we can see the application that, okay, that means we have the resonance arrow, over here, and we have 1, 2, double bond O, O minus double bond O. That means this particular case, we can see we have a two resonance structure, 1 and 2. So if you have more resonance structure, that particular structure is more stable. The why? Because once you leave H plus from here, if the negative charge somehow can be participate in the conjugation, I mean can be balanced with the molecule, right? So because if we have a negative charge over here, but because of C double bond O, it can easily stay over here. So that's why effect of resonance. But this particular conjugate base, there is no there is no conjugation. Do you have any conjugation? We don't have conjugation, right? This is sp3 carbon. So how we can move? So this electron cannot move from the over oxygen to another place. That's why comparing these two conjugate base, so if you compare these two conjugate base, 1, 2, the stability 2 is greater than 1. So that's why I mentioned, take a short note that higher the stability of conjugate base, corresponding acid is more acidic. So comparing the conjugate base, now we can see the stability, the acidity order. Is it clear, guys? Anybody question, please?
It's clear.
Yes, one question. Sorry. What did you say that it meant? Like if you had additional conjugate bases, if you had more resonant structures, that I mean that it was more acidic? Is that what you said?
More stable.
More
structure.
stable. Okay, gotcha. Okay, thank you.
So we realize the effect of elements, how the conjugate base stability based on their acidity matter. Now here we are seeing in terms of resonance that how it affects the acidity. So the structure molecule 2, the molecule 2 basically we can see we have a option of resonance. That's why the conjugate base is a stable than the other conjugate base. And I already mentioned that higher the stability of conjugate base, higher the corresponding acid is the higher acidity. Clear? So we understand these two factors, effect of element, effect of resonance. How about inductive effect?
So the comparison between the two conjugate bases, we're saying that the second one is more acidic than the first one, correct? In the top right-hand corner, the second structure is more acidic than the first structure.
No, we are not saying acidity. Here we are talking about stability.
Oh, okay. Okay, thank you.
Yeah, so stability is higher for 2 than 1 because of the resonance, right?
Wait, why is it more stable again? Sorry.
Because of the resonance.
Oh, okay.
So you don't have any resonance opportunity for conjugate base 1, right?
Oh, okay, yes. Okay.
So we realize two factor, inductive effect as well as, sorry. We realize element effect and resonance effect. How about inductive effect? Let's see. So this versus this. Which one is more acidic? Anybody?
The second one.
Yes, very good. So this is 1 and this is 2. So the acidity order 2 greater than 1. And why? Now think about whatever I show you. OH, F, 1, 2, 3, double bond O, OH. Now that means you have inductive effect over this direction. And here, this direction. Make sense? So now if we have inductive effect and after bond dissociation, what we get over here, O minus F, acid conjugate base, and here F 1, 2, 3, double bond O, O minus, plus H plus, plus H plus. Now consider this is a conjugate base 1, conjugate base 2. Now which one is more stable? Anybody? So here you can see two factors are there. One is this electron can participate in the conjugation as well as a fluorine also can stabilize the electron. But compared to this one, here it is higher because here fluorine is close to that negative charged atom, right? Negative charged element over here. So because fluorine close to, it can easily stabilize this negative charge, excess charge over oxygen because the fluorine can pull electrons to the bond. So the negative charge can be stabilized greater than this one. So two factors. One is resonance factor, same time inductive. But here, the distance from oxygen negative charge fluorine is greater than this one because 1, 2, 3, 4, 1, 2, 3, 4. Okay, so distance is same, but extra factor, which is resonance, that makes conjugate base more stable than that one. So acidity order, this one. Make sense? So if we want to understand the inductive effect, I think I already discussed that example over here, right? Here the position of chlorine. So because you have this particular case, you have chlorine close to that OH bond, so negative charge that can be stabilized using the electronegative effect, inductive effect. That's why. So you can see over here the pK values. So whenever I decided using the inductive effect that I said this is the order, also you can see the pK value 2.8, 4.1, 4.5. What I said, the lower the pK value, higher the acidity. Also you can see it's matching, right? Means whatever I discussed. So 2.8 means this should be higher acidic. So whatever pK value, okay. So now, so so far we have discussed the major four factors. One is three factors: element effect, hybridization, inductive effect, and resonance. How about the hybridization effect? Okay, now we want to see hybridization effect. Okay, so we want to see hybridization effect. So now, so these are basically structure 1, 2, 3, 4. So let's say if we have this one, okay, so this one negative plus H plus. Now this one negative plus H plus. Now this one sorry, negative plus H plus, and this one negative plus H plus. Now you might be asking that how, what I'm doing and what is going on. So this carbon you have 3 hydrogen. Let's do 1 hydrogen. This carbon also have 2 hydrogen. Let's 1 hydrogen over here. This carbon you have 1 hydrogen. This carbon you have 1 hydrogen, right? So basically, if you are breaking this bond, if you are breaking this bond, then you get H plus and corresponding conjugate base. This is conjugate base. If you break this bond, this bond, this bond, that means you are getting corresponding conjugate base, conjugate base, conjugate base. Correct. So now question is, we want to like see that how the hybridization effect on the acidity. So comparing these 4 molecules, 1, 2, 3, 4, which one is more acidic? So if I want to decide which one is more acidic, we have to consider the stability of the conjugate base. So which one is more stable conjugate base? Okay, that we have to decide. So now that means we have to compare the conjugate base stability. What I said again, we have to compare the stability of conjugate base. So how we'll compare the stability of conjugate base in terms of hybridization effect? So here, this carbon, what is the hybridization? sp3, this carbon sp2, this carbon sp, this carbon is sp2. Hybridization of carbon. Now, if that is the case, what do you know? If it is a sp3 carbon, the S character, percentage of S character, 25%. Here, SP 33.3%. Here, 50%. Here, 33.3%. S character. So if we have a hybridized orbital sp3, that means this particular carbon is sp3, you have 25% S character. sp2 33. So now the concept is, if we have higher the S character, that particular carbon nucleus is more stable, because you have compare all those carbons here, 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 here. Both are all 4 having negative charge, but there is a difference of hybridization. So that means negative charge can stay over here more stable because of the greater S character. right? So that means you have to think about s orbital and p orbital. So s orbital can pull electrons like closely than the other, like p orbital. So higher the s character, that means the negative charge can be more stabilized over this carbon than this carbon. This carbon is more stabilized than this carbon. So all this based on the s character. So that means you have very simple sp3 means, so 1s 2s and 2px 2py and 2pz. So each are, so that means sp3 means each are 25 25 25 25, right? Think about total 100%. So based on that we can calculate that percentage of s character. So that means what I want to say ultimately, that comparing conjugate base, this one is most stable conjugate base. If this one is most stable conjugate base, corresponding acid will be higher. So that means the 1 2 3 4, 3 is more acidic, then 2, then 1, then 4. That's the acidity order. Okay, so that means if we arrange those 4 molecules 1 2 3 4, that's the acidity order in terms of, hybridization effect. Because of, as I mentioned, that based on the conjugate base stability we decide. Questions, anybody? So we discuss 4 different factors, how it work.
Yeah, I got a quick question.
Yes.
I can't remember if you, I don't know if you, I was wondering why 4 was these tests.
Okay, I understand. Okay, that is a natural question. So that means actually that's the benzene ring. Already the electron rich. Okay, so that particular system is a benzene ring, so already electron rich, and it will prefer to have another negative charge over there. That is why. That's a different type of system, not an aliphatic system. Okay.
Okay.
So as well, actually, real quick, how did you place 2 ahead of 1 if they're both the same percentage of S?
One moment. You're talking about this one and that one?
Yes. Like, how did you rank them?
So because this is the carbon which is sp2, and this is the carbon which is sp2. Hybridization, sp2 hybridization. Make sense?
Right. So like, why is 2 ahead of 1 whenever you rank them, or does that matter? Are they interchangeable?
So why this is higher acidic than this one, right? I mean, why this is more stable than that one, right? That's the question, right?
Yes.
So if that is the case, as I mentioned, that we have 2 types of compound, aliphatic and aromatic. So this is the aromatic system. We have to have knowledge about aromatic system, that this is already electron rich system. So you have 3 pi bond 6 pi electron, already electron rich system. So but here you don't have that kind of function, right? So because of that, the negative charge is not that popular to stay here than this one. So this is already electron rich system. So how he can accommodate the excess electron? Think about it a little bit. I'll explain those kind of example later. But my concept is that who can accommodate electron more, this sp2 carbon or this sp2 carbon? The question is, this sp2 carbon can accommodate electron more after removing H plus than this one, because this system is not such a electron rich system than this one, because you have a 3 pi electron, 3 pi bond 6 pi electron. So this is already electron rich system. So after removal of H plus, it's not favorable, no? So that's why. Okay.
I have a question. Like, will that always be the case? Like, will the aromatic system always be the least amount?
Yes, aromatic systems are highly stable, and they are nucleophile, because they have 6 pi electron, and in a conjugated system, and electrons are delocalized throughout the ring. So that is the case. Okay, so if we understand those kind of stuff, concept, now we can figure it out which direction equilibrium will shift. That's all about the 4 factor I discussed. So we can decide that equilibrium will shift towards left or right. That's the question.
Would it shift right? Because like the OH group will just dissociate. Is that correct? I don't really know.
Dr. Mina, I can't hear you at all.
Yeah, I can't hear you either.
I think you're muted.
Yeah, looks like he accidentally muted himself.
He can't hear us. We have to hit the raise hand button in the bottom right. This happened in one of the review sessions the other day.
I still can't hear him.
I know, that worked last time.
One moment. Give me a moment. I understand. You guys are disconnected. One moment. Let me rejoin. Let me rejoin. So
We can hear you fine now.
let me share the screen and 96903 9690373 2131. Okay, can you hear me?
Yes.
Okay, perfect. So what I was saying that if I want to find out that which direction equilibrium will shift, first let's take this molecule, ethanol, and if you remove H plus, we get corresponding conjugate base, and this is sodium plus a counter ion, right? Now if you take this one, CH3, COOH, so this will dissociate, we get a CH3, COO minus plus H plus, and if we have like a counter ion, Na plus over here, right? So now we have to decide which direction equilibrium shift. Ultimate goal, we have to find out that between CH3, CH2O minus and CH3, COO minus, which one is more stable conjugate base? If we can figure it out, yes. So if we can figure it out which one is more stable conjugate base, that means that direction equilibrium will shift. I repeat again. If we can figure it out between these two conjugate base, which one is more stable, that direction equilibrium will shift. Why? Because comparing, so that means which is more stable? Anybody? 1 and 2. Which one is more stable conjugate base?
2.
Absolutely 2, because 2 you have opportunity of resonance, right? So that's why 2 is more stable conjugate base. If 2 is more stable conjugate base, that means this one is more stable conjugate base, so equilibrium will shift this direction towards left. Okay, so this particular case equilibrium will shift towards left. Why? Because think about in a certain amount of time, like the way like acetic acid giving H plus and CH3CO2 Na plus, and the same time CH3CH2O is ethanol giving this conjugate base and H plus. So which is faster? So acetic acid is faster because of the stability of conjugate base. So a more stable conjugate base. So this direction equilibrium will shift. Make sense? So in terms of resonance, once we figured out which one is more stable conjugate base, that direction is equilibrium will shift. Let's take one more example so it will be easy. So let's say this one, last one. Let's say this one, try about this one. So which direction equilibrium will shift, right? So that means if we have OH, so if we dissociate, we get O minus and we get H plus. And if we have this one, OH, if we have equilibrium, we get O minus and plus H plus. Now, this is the conjugate base for this acid, and this is the conjugate base for this acid. Now, which one is more stable? Anybody? Which one is more stable conjugate base? Anybody? The one on top or one on bottom?
One on the
That's
top.
on the
Top.
top. Very good. Yes, yes, absolutely. Very good. So that's why last 1 week I'm just spending time on resonance, because now you can see that here, this particular, this guy, negative charge come over here, this will come over here. So next resonating structure, double bond O minus over here, here again, this will go over here, this electron, double bond minus. Now this will go over here, this guy come over here. Make sense? So that means in this particular conjugate base, you can have a resonance structure, right? So that means this is more stable, but here you don't have any chance to how to do resonance. Why? Because there is no p orbital double bond. Is it interesting now? Now you understand why I was like spending 1 week on resonance. So those are the basic stuff. Now you can apply over here. If you have understanding that, okay, how to rotate the electrons from one atom to another atom, that you have a chance of resonance in this conjugate base than this one. And I already mentioned that if the conjugate base is more stable, the corresponding acid is more acidic, right? And also I mentioned that the conjugate base stability. Okay, so that means equilibrium will shift left or right?
Right.
Yes, very good. Equilibrium will shift towards right. So this direction, right. Okay, so equilibrium will shift towards right, because the point, given point of time, this one giving H plus, same time this one also giving it is called phenol. This is called phenol. So then every compound we have a name, right? Common name, IFAC name will go later. But for now, this is phenol and this is cyclohexanone. So the particular time, the phenol giving H plus, and the same time cyclohexanol giving H plus. Who is giving more H plus? Phenol, because the conjugate base is more stable. That's the equilibrium favor towards right. If we understand, now we can try all those examples. But think about where we have to use what kind of factor. Like 4 factors we have: hybridization, element effect, and we also have 2 more: resonance and what is the other one? Inductive effect. So we have to think about where you can apply the 4 factors to decide the stability of conjugate base, and then you can figure it out the which direction equilibrium will shift. Okay, so this is all for today. Keep practicing, and definitely now we'll start practicing more questions. And organic chemistry, that's the only best way to kill, that is practicing problems. Okay, so last thing, just couple of minutes please. So because this is very important, because we started from scratch, so we have to know this kind of stuff. One moment.
Dr. Mana,
Yes, please.
can we go over some like more examples like tonight during like the evening session, just so we
Yes, that's my plan. Yeah, that's my strategy. Yeah, of course I have like more examples, and already I just explaining few examples right now, and then we'll discuss more in the evening. Okay.
I'm sorry,
Thank you.
what days are the evening sessions?
9 o'clock.
What days? Is it every day?
Every day, yes.
Oh, okay.
Every day, yes. So now I want to show you something very important, because we have started from scratch. So okay, so that means based on our knowledge of hybridization, covalent bond, major atoms, hydrogen, oxygen, nitrogen, and carbon, now we can classify organic molecules in different class. So we have millions of molecules, but in general, so like in the common molecules, we have a classification of organic molecules. Okay, so what we see here, that these four class of molecules, they are hydrocarbon. The compound or molecule made up of carbon and hydrogen we call hydrocarbon, but based on the structural feature we have a name: alkane, alkene, alkyne, and arene. That's the aromatic okay. So if you don't have any double bond, that is called alkane. If you have at least one double bond present in the molecule, we call alkene or olefin. If you have at least one triple bond in the hydrocarbon, we call alkyne. If you have a cyclic system, fully conjugated, 4n plus 2 pi electron, and planar, we call aromatic system or arene. So these are the four hydrocarbons. Okay, so that means we have to recognize, we have to understand what class of molecule it is. Now, if we have a halogen, fluorine, chlorine, bromine, iodine, if they are directly connected with a carbon sp3, we call alkyl halide. If we have a OH, we call the functional group alcohol. If this is connected with a carbon, if we have a oxygen, like carbon, oxygen, carbon linkage, that actually ether. Now, if we have a OH with sp2 carbon, we call enol and corresponding enolate. Now, if we have two OH, we call diol. If we have a three-member ring with the oxygen, one carbon, we call epoxide. If we have SH connected with the carbon thiol, if we have S alkyl groups, we call sulfide. Now, if we have C double bond OH, that we'll call aldehyde. If you have C double bond O, called ketone. If you have C double bond O bond OH, carboxylic acid. If we have C double bond O Cl, acyl halide. If we have C double bond O C double bond, if you have this kind of bridge, that's acidic anhydride. If you have C double bond O CH3 ester and C double bond H2 amide. Besides that, we have few more. So we'll repeat it just because I said that we should have all those information for working of those kind of examples. So make sure that we have some common idea. Okay, the molecule can be classified based on the functional group. So that means alcohol, ether, aldehyde, ketone, carboxylic acid, those are the functional group. Ester, anhydride, amide, cyanide, amino, nitrile, those are the functional group, and we can classify those molecules, right? So what we learn in this particular course, we learn about a specific class of molecule: alkane, alkene, alkyne, acyl chloride, and yeah, these four things we learn in this organic chemistry 1. Now if you go to organic chemistry 2, there you will learn about aldehyde, ketones, carboxylic acid, or other stuff. Oh yes, we also have a chance to learn about alcohol, ether, and alcohol ether epoxide. So this is called epoxide, this one. So that means in organic chemistry 1, we have a chance to learn details about alkane, alkene, alkynes, these three class of molecules, and then acyl halide, 4th, alcohol 5th, ether 6th, and epoxide 7. We don't have any opportunity to talk about arene or all those stuffs you have in organic chemistry 2. So what is the trend we'll follow after having fundamentals, that how we can synthesize those molecules, what is the reactivity, how they react, different type of substrate, and we'll discuss those kind of stuff. But before that, we have a stereochemistry, spectroscopy. We have to have fundamental knowledge. All right. So thank you very much, everybody, and keep joining so that like practicing, and that's the only, I mean, I'll make you success. So don't worry about any exams or quizzes or assignments. So try to understand, enjoy the chemistry. Okay. So anybody questions, please?
Will you be posting the slides later?
Yeah, definitely by tonight. Okay. Thank you for asking. Okay.
Thank you.
Dr.
Yeah.
Manna, when
Yes,
it
please.
comes to the induction effect, when the chlorine is more closer to the O negative, that means the induction effect is higher and the structure is more acidic, right?
Yes, yes, correct.
Okay.
Bye, guys.
Thank you.